So one of our favorite problems to study in physics is the harmonic oscillator. We do this in intro physics, we do it in upper level classical mechanics, we do it in relativity, we do it in quantum mechanics. The reason we love the harmonic oscillator is because you can exactly solve it in so many different arenas. And so anytime you come up with a new technique, a new perturbation theory, a new approximation technique, some new thing to do with physics problems, you always test it on the harmonic oscillator first because we know what the answer is, it behaves well, and it ends up approximating so well so many times. You might remember that this is the problem where you have a potential energy that's given as 1/2 some kind of spring stiffness times your distance from equilibrium squared. So this is the problem of a spring. Your potential energy gets higher if you have a stiffer spring or if you move farther away from equilibrium. This is how you end up rolling downhill, right? This is shaped, the shape of this is pretty straightforward. It's a parabola. So classically, you're going to tend to roll downhill toward equilibrium. Then you overshoot equilibrium. You end up back at the same height that you were before. In quantum mechanics, we're going to rewrite this a little bit. It turns out to be a little more convenient to write this k in terms of the angular frequency. So you might remember from classical mechanics, this thing oscillates back and forth with an angular frequency given by root k over m, where m is the mass of this, well, in our case, an electron going back and forth here. So that just means this is going to be 1/2 m omega squared x squared. You rearrange this for k, you end up with m omega squared. And so it's just more convenient. You'll see why in a minute when the math ends up working out a little bit better. Solving this in quantum mechanics is something we can do exactly. It's probably detailed in your quantum mechanics textbook. It's definitely detailed in about 1.5 million class notes out there on the internet. So I'm not going to repeat it because you can read about that. But the end result is you get a set of energy levels, right? We need our energy eigenvalues to study our energy eigenstates, right? Those are important. That's a pretty simple formula. It's equal to the level number plus 1/2 times h bar omega. So here's Planck's constant, here's this omega, and that's why we like to write this in terms of omega, because it's only the omega that gets spat out there. The m is hidden inside here, right? So we're not having to worry about the k and the m separately. It's just the omega. So you've got a quantum here. You've got a lump of h bar omega, and for each energy eigenvalue that you go up, it increases by another one of those. I should probably mention this n starts at 0 and goes up through the positive integers, right? So we're not allowed to have negatives on this thing. The energy eigenstates themselves are a wonder to behold. They've got 3 pieces to them. We're going to look at each one in turn. First, there's a normalization constant that does depend on n, right? That's a constant. It's just there to make sure that the total probability under the energy eigenstate is 1. So don't get scared by it in a second. It's just a constant. We then take an exponential, right? So e to the something. A lot of folks will write exp, meaning e to the something, just to avoid having to write that tiny script up there in the exponent. You put in a negative m omega over 2h bar, right? All constants we've seen before. Then times x squared. So this whole thing has an overall shape of a Gaussian, right, of e to the negative x squared. That's the overall shape. It's about to get modified. But as you work with these things, just remember they've got an overall kind of envelope of this e to the negative x squared. The next part is a function called a Hermit Polynomial. It's just a polynomial. You know what a polynomial is, right? It's some number plus some number times x plus some number times x squared plus some number times x cubed plus some number times x to the 4th, however high you want to go. The Hermit polynomials is just a special combination of those coefficients that give you the right polynomials that end up solving the Schrodinger equation for the harmonic oscillator potential energy. Inside the argument for this is the position x. But the Hermit polynomials have to accept a dimensionless number, so we have to scale out the units of meters with an m omega over h bar. So you do the units on this. This thing will have units of 1 over meters. This has units of meters, so those cancel. You just have a pure number going to hn, kind of like you have to do with a sine and cosine. So the first piece of this, the normalization constant, has a few pieces to it. There's going to be an m omega over pi h bar. You keep seeing this combination of m omega over and over again. That all gets raised to the 1/4 power, right? Just to make the units work out, it's got to be a 1/4 power. then that gets divided by a number, because these Hermit polynomials, they tend to grow and become more complicated as n increases. So we need something that kind of scales that down. So we need something that increases with n. It turns out the combination that works is the square root of 2 to the n times n factorial, right? So you know how to take 2 to the n, right? It's going to be 1, 2, 4, 8, 16, et cetera, et cetera. And then n factorial is just n times n minus 1 times n minus 2, et cetera, all the way down to 1. Or 0 factorial is 1 for reasons that I'll leave other YouTube videos to explain. But again, this is just the normalization constant. This is just the number you need out in front to make sure that when you take integral of psi n star psi n dx, you end up with 1, going from minus infinity to infinity. Right. If you leave this off and you just take the integral of this piece, you end up with this thing flipped upside down and squared, which is why this thing has a 1/4 and this thing has a square root. So you take the square root of that thing that you get out, you flip it upside down, that becomes your normalization constant. By now you should have done some normalization problems in your quantum mechanics class, I'm guessing. Okay, the next piece is the Hermit polynomial. So Hn, I know this is a little bit complicated here, there's a lot to write there, so we're just going to call that whole thing z. So z is going to be just a dimensionless number. So Hn is what we call the nth Hermit polynomial. Basically, if you're a physicist or mathematician and you work with a function enough, you can get that function named after you. That's why it's the Hermit polynomial. The way you can get these, there's a little generating function for these. There's all sorts of ways to get these. There's recursion relations, there's a pattern in the coefficients, etc. One of the most straightforward ways to get this is through some derivatives. So you start out with a -1 to the n. So that's just going to alternate +1 or -1, right? So for n equals 0, that's going to be a +1. For n equals 1, it's going to be a -1. For n equals 2, that's going to be a +1. For n equals 3, it's going to be a -1. It's just alternating the sign. That's important. Then you have an exponential of z squared. You say, I thought the thing was a polynomial. This is not a polynomial, right? So we need to cancel it with another exponential later. Then you multiply that by the nth derivative of exponential -z squared. Right? So you know how to take the derivative of an exponential function, right? You just spit out the same function and then you take the chain rule, you take the derivative of the inside, and so that's why this exponential cancels out with this exponential after you've taken n derivatives of it. Let's take a look at one or two of these Hermit polynomials just to get an idea of what they look like, because these two pieces work the same way for every state psi n that you're looking at. An just has this denominator increase. This piece always stays the same. It's the Hermit polynomial that really makes these things shaped differently. So why don't we try an easy one first. Let's try h0 of z. Right, so this is going to be -1 to the n, right? I start out with this, exponential of z squared times the 0th derivative, so d0 dx0 of exponential -z squared, right? So it's easy to work with 0, right? So this is just going to be a 1 times exponential z squared. And you say, what is the 0th derivative? Well, if you take 0 derivatives of a function, you haven't done anything to the function, so it is the original function. So this is just exponential -z squared again. You have thing times thing to the -1 power. So these two will cancel, giving you 1. And you're left with just 1 times 1 equals 1. So your h0 of z is 1. And I know what you're thinking. This is a complicated way of saying this equal to 1. Well, the power comes in when you want more advanced numbers here. So let's try h1 of z. So that's going to be -1 to the first power, exponential z squared. That's always the same. Then first derivative of this exponential -z squared. Okay? -1 to the first power, that's going to be a -1. So the overall thing has a minus sign. I got this exponential z squared. I take a derivative of this thing. Well, exponential gets left alone, right? That's the easiest thing to differentiate and integrate. And then I need to take the internal derivative here, right? I need to take the derivative of negative z squared. Well, that's going to be a negative 2z. It's just the power rule, right? Well, again, these two cancel. So that'll equal 1. And so the whole thing, I have a negative times negative 2z. I get an h1 of z is 2z. And so the reason you go through all of this machinery, so like when you get down to h11 and you're taking 11 derivatives of this, have fun with that. The reason you do all that is to get out these coefficients, right? It's the coefficients that make one polynomial different from another polynomial. And so the Hermit polynomials are there to guarantee that you get the right coefficients in this wave function so that you can solve the Schrodinger equation for the harmonic oscillator potential energy.
So here we've got our n=1 stationary state for the harmonic oscillator. We have picked n=1. We've set up our normalization constant here. It's got all the features that we had on the board. And then our psi is just a times this exponential function times a Hermit polynomial. The way we're doing the Hermit polynomial is with the recursion relation. So the way I showed you on the board is one way you can get it, but I, for one, am not sure how to get Python to do those derivatives. So this recursion relation is a nice, easy way to do it. Once you know what n0 is and what n=1 is, you can end up generating these just with a recursion relation here, just referring back to the previous two. And so you can see we get a nice stationary state. The real and imaginary parts are evolving. They're trading probability back and forth, but the overall modulus, this overall envelope, has to remain the same. And that's going to be true no matter how high we go up in the states. So we're going to go up to n=3 here. And so you see we get a nice stationary state going over there. Now, the fun part, of course, comes in when you make a combination of these. So, for example, let's suppose we start with a n=1. So let's actually, an n=1. So we'll call this one psi1 equals all of that. Then we'll repeat it for n equals, let's say n=2. And so we'll repeat all of this stuff. We'll call this one psi2, and we'll make psi real initial equal to psi1 plus psi2. We are going to need to normalize that. So let's see, each of those is normalized to 1 already, so we'll just divide by square root of 2. So we've got an equal piece of psi1 and an equal piece of psi2. So you see it's no longer symmetric here, right? Because we've got a little bit more weighting to the right than we do to the left. And also this is no longer an energy eigenstate, even though psi1 is an eigenstate and psi2 is an eigenstate. When you combine them, it's no longer an energy eigenstate. They're no longer attached to a unique eigenvalue. And you can see that already we've got a little bit of time evolution going on in this intermixed state here. And if you scroll down, we can look at the expectation values. They're, of course, going to obey the classical law that this has to oscillate like a cosine, and the momentum has to oscillate like a sine function. And of course, you can have as many of these states here as you want. So for example, if we use what we learned about Fourier's trick, I can have a list of coefficients equal to maybe 1, 0, 2, 4, 5. And then what I can do is say for, let's do for n in range 0 to the length of the coefficients. I can take this whole thing, copy and paste it here. Tab that in. Let's see, we can start with psi real initial equal to 0. And then basically each time here, we're just going to add the next contribution here. So I'm keeping track of n here. I'll need to multiply by my coefficient of the current index. Right, so we'll loop over 0, 1, 2, 3, 4. We'll get a total of 5 of these added together, and then we'll return psi 0. Now, I haven't normalized these coefficients. I believe I have the code set to automatically normalize later. Yes. So we do automatically normalize the wave function, so I should not have to worry about that. We'll see if I'm right about that. And there we go. There is our wave function made of 1, 2, 3, 4 different energy eigenstates. And yeah, you can set up these coefficients however you want and watch this thing evolve. And again, you can see no matter how complicated we make this wave function, the expectation values still have to obey classical laws.
But wait, there's more. It turns out that these psi-n's, these energy eigenstates of the harmonic oscillator, allow you to form a very special type of state called a coherent state. You don't get to do this with the energy eigenstates of just any problem. So you don't get to do this with the eigenstates of the infinite square well or the Dirac delta function or any of that stuff. Coherent states are wonderful. They are good for everything, as one of my graduate school professors would say. The way you form a coherent state is you pick a number alpha. And the beautiful thing about this is this can be any complex number. And you just get to pick one based on whatever properties you need the coherent state to have. You just pick this value alpha here, and you can form a coherent state psi alpha. Right? So this psi, this is an energy eigenstate. It's labeled by an integer. This is not an energy eigenstate. It's not going to spit out a particular energy value. And it's labeled by a complex number. So we're going from the integers to the complex numbers here. We're just skipping right past the reals. The way you formulate this is you take another exponential. That seems to be important with these harmonic oscillator states. You take negative modulus alpha squared over 2. Right, this is just, again, normalization constant. Make sure the whole thing comes out to total probability of 1. Then you sum over all of the harmonic oscillator energy eigenstates. You sum over all of these psi-n's that we figured out over here. You take this as alpha to the n divided by square root of n factorial. Right? So this combination here ensures that this thing stays normalized, so the total area underneath the modulus squared is 1. And this thing has some really neat properties. We're going to play around with these in the code at the end of the video. We're going to see that it kind of maintains its shape in the harmonic oscillator potential. It stays coherent, hence the term coherent state. The other thing that this does is that it keeps the Heisenberg uncertainty principle at a minimum. What does that mean? Well, you remember the Heisenberg uncertainty principle says that your uncertainty in a measurement of x times your uncertainty in a measurement of p, really it's the distribution of the state, we know that now, has to be greater than or equal to h bar over 2. Well, the coherent states keep this at the minimum value equal to h bar over 2. So a coherent state, in a sense, is the most accurate state you can have in terms of measuring x and p. We'll take a look at what that means at the end of the video.
So here we've got our coherent state set up. We've chosen a value of alpha equal to 1/2. We've got our summation over psi real to end up with the total psi. We've got our calculation of psi n, just like we had before. I have fixed an issue I had previously. I forgot to multiply by the square root. It didn't matter because m omega and h bar were all equal to 1, but now I've gone back and added those up here just to correct that. So here we've got the summation that we had on the board. We've got alpha to the n over square root of n factorial times psi of n. And so now all I need is to normalize this by multiplying psi real 0 by exponential negative alpha squared over 2. There we go. And so we'll click run on this. We'll get out our coherent state. You can see it looks like a Gaussian kind of curve, which is basically what you're summing these up in order to get. And again, this thing will maintain its shape. It's going to maintain its coherence as it bounces back and forth. Again, our expectation values are going to obey classical laws, and we can watch this thing bounce back and forth. So you can see the other wave functions we've looked at, they would have kind of broken up by now. They would have gotten all wiggly, they would have developed multiple peaks, but the coherent state stays coherent. It stays in this Gaussian shape. And basically the width of that is determined by this alpha, right? So if I make this a 0.1 instead of a 0.5, that's going to change the width of it. It's going to change the where it's centered, but it's always going to maintain that shape, and it's always going to maintain a minimum of the uncertainty between position and momentum.